Hello students, this is Dr. Srinivas Keshetti. Welcome to the third session on Unit 2, Classical Statistics and Quantum Statistics. In this lecture, we will study what is Bose-Einstein statistics. In the previous two sessions, we have studied what is meant by phase space and Maxwell-Boltzmann statistics. Bose-Einstein, isn't it? So, we have studied what is a Maxwell's Boltzmann statistics. It is applicable to certain class of kinds of particles like differentiable particles, isn't it? Here, uh, we are going to deal with the identical but indistinguishable particles, isn't it? So Maxwell-Boltzmann statistics can explain certain characteristics, certain properties of ideal gas like temperature, pressure, etc. But it fails to explain the black body radiation or the behavior of specific heat of materials at low temperature and certain other properties, isn't it? So in order to explain these properties where the Maxwell-Boltzmann statistic fails, we require some other kind of statistics which was proposed by Satyendranath Bose, an Indian scientist, along with Albert Einstein. Both of them proposed this statistics, which is called the Bose-Einstein Statistics. It was proposed in 1924. The statistics is applicable to identical and indistinguishable particles. Here the particles are identical, but they are indistinguishable. We cannot distinguish between the particles which is particle A, which is B, and which is C. You can imagine a room full of balloons which are flying from one place to another place and which are of suppose same size and they are of same color. They are of same size and they are of same color, isn't it? So if there are number of balloons flying from one position to another position, you cannot distinguish between which balloon is balloon number one or which you cannot distinguish. They are indistinguishable, isn't it? So uh, such such a situation, for such a situation where the particles are identical and indistinguishable, having zero or integral spin, isn't it? So the particles having zero or integral spin. So, Bose-Einstein statistics is applicable to identical indistinguishable particles having zero or integral spin. These particles do not obey Pauli's exclusion principle, isn't it? So these particles do not obey Pauli's exclusion principle. Pauli's exclusion principle states that no two electrons can occupy same energy state, or no two electrons can have all the four quantum numbers same, isn't it? So this is called as Pauli's exclusion principle, and this principle is not obeyed by the certain particles like photons, phonons, or Cooper pairs, isn't it? So for such type of particles, Bose-Einstein statistics is applicable. There is no restriction on number of particles occupying same energy state. Here another condition is that there is no restriction on number of particles occupying same energy state. Here the any number of particles can occupy same energy state, isn't it? So there is no restriction on number of particles occupying same energy state. The particles obeying such type of statistics are called bosons, isn't it? So in the name of Satyendranath Bose, the particles which are obeying such statistics are called as bosons. Example, photons of light, isn't it? Which are identical and indistinguishable and possess zero or integral spins. Or phonons, isn't it? The particles carrying heat energy from one position to another position. Or mesons, like that, isn't it? So such type of particles obey Bose-Einstein statistics, isn't it? Here we can imagine uh, the situation of the particles which are obeying the classical statistics, that is Maxwell-Boltzmann statistics, Bose-Einstein statistics and Fermi-Dirac statistics, isn't it? So here the particles are distinguishable. They are shown by P and Q, isn't it? So P is in the first compartment, Q is in the second compartment, or Q is in the first compartment, P is in the second compartment. So we get four different types of microstates for arranging two particles in two particles in two compartments, isn't it? So we get four microstates, isn't it? Then for Bose-Einstein statistics, the particles are indistinguishable. We cannot distinguish whether this particle is A or this particle is A, isn't it? So this may be A and this may be B, or this may be B and this may be A, isn't it? So these particles are identical but indistinguishable. So and these particles can any number of particles can occupy same energy state. So these two particles can occupy a single compartment, isn't it? So we get three different types of microstates if the situation is that the particles are identical and indistinguishable, can occupy any number of particles can occupy a single energy state. This is Fermi-Dirac statistics. Here again particles are identical and distinguishable, and one more condition is that uh, uh, no two particles can occupy same energy state. So we can say, in other words, no two particles can occupy a single compartment. So each particle has to be occupied in the separate compartment. So depending upon the nature of the particles, we can apply different types of statistics. Okay, this is classical or Maxwell-Boltzmann statistics. If the particles are in certain types of characteristics, isn't it? Identical, distinguishable, isn't it? And can occupy uh, uh, there is no restriction on the particles occupying same energy state. We get four microstate. Here for bosons we get three microstate. For fermions we get only one microstate. So we the number of microstates depends upon the nature of the particle. So the most probable distribution and the thermodynamic probability also goes on changing, isn't it? What is thermodynamic probability? The number of microstate within a macrostate divided by total number of microstates, isn't it, of the system, isn't it? So that is called as thermodynamic probability. So the thermodynamic probability goes on changing. So naturally the most probable state also goes on changing, isn't it? That is why we need different types of statistics. Now let us study what is Bose-Einstein distribution law. Consider an assembly of n bosons. let us consider an assembly of particles obeying Bose-Einstein statistics. They are n in number. They are identical and indistinguishable, isn't it? There is no restriction imposed as to the number of particles that can occupy a given cell. So there is no restriction on the number of particles occupying a particular energy state. Let us now consider a box divided into GI sections by GI minus 1 partitions, isn't it? So if you put a partition in a box, isn't it, it gets divided into two compartments. If you put two compartments in the same box, one aside other, the box is divided into three compartments. So each compartment, the if any box contains n number of compartments, then the the number of partitions is n minus 1. Here also the same thing is given. Let us consider a box divided into GI sections. So the box is divided into GI sections by GI minus 1 partitions, and n1 distinguishable particles to be distributed among these sections. So So in this GI sections, we are going to distribute how many particles? Ni particles, isn't it? The permutations of Ni particles and Gi minus 1 partitions simultaneously is given by Ni plus Gi minus 1 factorial. The permutations of Ni particles and Gi minus 1 partitions simultaneously is given by Ni plus Gi minus 1. But this includes also the permutations of Ni particles among themselves and also Gi minus 1 partitions among themselves. It includes what? The permutations of Ni particles among themselves and Gi minus 1 particles among themselves. As both these groups are internally indistinguishable, these groups are both internally indistinguishable, hence the actual number of ways in which Ni particles can be distributed in GI sublevels is given by here. The actual number of ways in which Ni particles are to be distributed in GI sublevels is given by Ni plus Gi minus 1 factorial divided by Ni factorial into Gi minus 1 factorial. So this is for one section, one energy level, isn't it, where there are we have to distribute Ni number of particles in Gi sections having Gi minus 1 particles. But there are total n number of particles. We are going to distribute them in different energy states, isn't it? In the energy level having energy E1, suppose there are G1 number of particles and N1 number of atoms to be distributed, isn't it? G1 number of partitions, sections, and N1 number of particles are to be distributed. So in such a way, suppose we consider an energy level E1 having G1 number of partitions and N1 number of atoms to be distributed in this energy state. There is again energy level E2 where there are N2 number of particles and G2 number of sections. So N2 number of particles are to be distributed in this G2 sections. Similarly, energy level E3 having G3 partitions, G3 sections, not partitions, sections, and we have to distribute N3 number of particles in this G3 section. Similarly, there is a energy level EI having number of sections GI and Ni number of particles are to be distributed in this GI sections, isn't it? Like this, isn't it? So therefore the total number of distinguishable and distinct ways of arranging n particles in all the variable energy states is given by W is equal to product of pi of ni plus gi minus 1 factorial divided by ni factorial into gi minus 1 factorial. Here, Ni and Gi are large numbers. The number is very large, 10 to the power 28 suppose, isn't it? Since we can neglect this minus 1, isn't it? So we may neglect minus 1 from the above expression. So Gi minus 1 is nearly equal to Gi. Ni plus Gi minus 1 is nearly equal to Ni plus Gi. Therefore W is equal to pi of Ni plus Gi factorial divided by Ni factorial into Gi factorial. This gives us the thermodynamic probability, isn't it? Now let us consider let Ni to be equal to 3. Number of particles is 3 and Gi is 2. Gi is number of sections, isn't it? So the particles are indistinguishable. There are only 2 sections. 3 particles are to be arranged in 2 sections. So we can arrange them in 4 different ways because they are identical and indistinguishable, like 3 particles in the first compartment, 0 particles in the second compartment, 2 particles in the first compartment, 1 particle in the second compartment, 1 particle in the first compartment, 2 particles in the second compartment, 0 particles in the first compartment, 3 particles in the second. So for Ni is equal to 3 and Gi is equal to 2, there are 4 microstates. There are 4 microstates, or we can say that the number of ways Ni particles can be arranged in Gi number of cells is this much, that is 4. That is given by this expression Ni plus Gi minus 1 factorial divided by Ni factorial into Gi factorial. Here Ni is equal to 3, Gi is equal to 2, 3 plus 2 minus 1 factorial divided by Ni is equal to 3, therefore 3 factorial. Gi is equal to Gi minus 1 is equal to 2 minus 1 is equal to 1 factorial. Therefore 4 factorial divided by 3 factorial into 1 factorial, which comes out to be equal to 4. 1 into 2 into 3 into 4 divided by 1 into 2 into 3 into 1 is equal to 4, isn't it? So we can express like this: Ni particles to be distributed in Gi number of cells, and that they can be arranged in this many number of ways, isn't it? Or for all the energy states taken together, that is N1 number of particles to be distributed in G1 number of cells having energy E1, N2 number of particles to be distributed in G2 number of cells having energy E2, N3 number of particles to be distributed in G3 number of cells having energy E3, and so on. Ni number of particles to be distributed in Gi number of cells having energy Ei, and that can be done by this relation W is equal to N1 plus G1 minus 1 factorial divided by N1 factorial into G1 minus 1 factorial into N2 plus G2 minus 1 factorial divided by N2 factorial into G2 minus 1 factorial, and so on. Ni plus Gi minus 1 factorial divided by Ni factorial into Gi minus 1 factorial, isn't it? Or W is equal to product of all these terms, that is pi of Ni plus Gi minus 1 factorial divided by Ni factorial into Gi minus 1 factorial. The product runs over I is equal to 1 to capital N. Therefore, if you take the natural logarithm of the above expression, which expression? This expression. Natural logarithm of this expression, we get log of W is equal to summation of log of Ni plus Gi factorial minus Ni factorial minus Gi factorial, isn't it? log of ni plus gi factorial minus log of ni factorial minus log of gi factorial. Also, ni and gi are large numbers. We can use Stirling's approximation, isn't it? Here let us use Stirling's approximation. What is Stirling's approximation? Uh, log of n factorial is equal to n log n minus n, isn't it? Here ni plus gi factorial can be written as log of w is equal to summation of ni plus gi log of ni plus gi minus ni plus gi, isn't it? Similarly for this, ni log of ni minus ni, here this is minus, so it becomes plus, minus gi log of gi plus gi. This plus gi plus ni, with here you get minus ni minus gi, it will cancel. So after cancellation you get this expression, isn't it? Here gi is subjected to variation. Gi is not going to change. The number of sections is not going to change. Therefore, gi is not subjected to variation. Ni varies continuously. So, for most probable distribution, log of W max, delta log of W max must be equal to 0. We have to derivative of this, and for getting the maximum value, delta log of W max must be equal to 0. For most probable distribution, delta log of W max is equal to 0. The treatment is same as the treatment that we met in the Maxwell-Boltzmann statistic, isn't it? Hence, for W, for the W of equation 3 represents a maximum, delta log of W max is equal to summation of log of ni plus gi minus log of ni into delta ni, isn't it? So as this is not subjected to variation, you get the derivative of this term to be equal to 0, because this is constant. So here log of ni plus gi minus log of ni into delta ni is equal to 0, isn't it? If you take the derivative and simplify, the total number of particles and total energy are constant, isn't it? Total energy is constant. Here total number of particles is constant. We have seen this in the Maxwell-Boltzmann statistics, and total energy is going to be constant. Ai into delta n is equal to constant. So we want the maximum value of this under the condition that delta ni, summation of delta ni, that is total number of particles, is constant and total energy is constant, isn't it? So under these conditions, we want the maximum value of this thermodynamic probability. So here again we will apply the method of Lagrange method of undetermined multipliers. Lagrange method of undetermined multipliers. So multiplying this equation by minus alpha, this equation by minus beta, and adding it to equation number 4, we get log of delta ni, log of ni plus gi minus log of ni minus alpha, this terms as it is, minus alpha minus beta ei into delta ni. We are taking this delta ni common, isn't it? So what we get, log of ni plus gi minus log of ni minus alpha minus beta ei into delta ni is equal to 0. So the variations of delta ni are independent of each other. So the variations of delta Ni are independent of each other. So this bracketed term must be equal to 0 in order to get the maxima of W, that is thermodynamic probability, isn't it? So equating this term with this 0, this bracketed term with 0, you get log of Ni plus Gi upon Ni minus alpha minus beta Ei is equal to 0, isn't it? So simplifying this equation, you can transfer this to right hand side, isn't it? And taking antilog of both sides, isn't it? What you get, Ni plus Gi upon Ni is equal to e to the power alpha plus beta Ei, isn't it? E to the power alpha plus beta Ei. Then you divide this term by Ni. Ni divided by Ni is equal to 1. 1 plus Gi upon Ni. 1 plus Gi upon Ni is equal to e to the power alpha plus beta Ei. So what you get? 1 plus Gi upon Ni, 1 plus Gi upon Ni is equal to e to the power alpha plus beta Ei. If you transfer this 1 to the right hand side, what you get? Gi upon Ni is equal to e to the power alpha plus beta Ei minus 1. E to the power alpha plus beta Ei minus 1. So Gi upon Ni is equal to e to the power alpha plus beta Ei minus 1, or you can write Ni is equal to Gi upon e to the power alpha plus beta Ei minus 1, or Ni is equal to Gi upon e to the power alpha e to the power beta, value of beta is 1 upon kt, so Ei upon kt minus 1. So this is called as the Bose-Einstein distribution law, which is most probable distribution, isn't it, for the particles which are identical, indistinguishable, having zero or integral spin, and any number of particles can occupy a single state. There is no restriction on number of particles occupying single state and the particles which are not obeying Pauli's exclusion principle. So the most probable distribution for such kind of particles is given by this expression. Ni is equal to Gi upon e to the power alpha plus beta Ei, alpha plus beta Ei minus 1, or this expression. So we come to the end of the session. So in today's session we have studied what is meant by Bose-Einstein's statistics or Bose-Einstein's distribution law, isn't it? So in the next session we will study the third kind of statistics, which is called as Fermi-Dirac statistics, isn't it? So till then, take care, have a nice time, isn't it? Don't forget to like our channel, subscribe our channel, like, share and comment on our videos, and press the bell icon so that you can get the notifications. Thank you very much.